Okay, so today's lesson is on a particular type of solution that we call a buffer solution that contains both an acid and its conjugate base. Well, let me change that. Both a weak acid, moderately weak acid, and its moderately weak conjugate base. Up to this point, and I've been doing this kind of review with you kind of orally for the last couple of lessons, right? We talked about strong acids and bases. They 100% ionize. We know how to use the pH and POH equation. So I'm not even considering that information new information, right? I'm hoping that we know how to calculate a pH, a POH, an H3O plus OH minus from our pH numbers. I'm just going to consider that as being tools that we have. So what have we really done in this particular entire unit? Well, we've essentially learned two equations. We've learned a shortcut equation that allows us to determine the H3O plus if we're dealing with a weak acid, all right, if the approximation is true. And we've learned the corresponding equation that allows us to find the OH minus if we're dealing with a weak base given the initial concentrations of that base and of that acid. All right, and there they are there. Those are really the only two equations that we've really learned here. And all we've been doing is simply applying them to different situations. And you'll notice I say here pure water, right? And what I mean by pure water is that there are no other ions in that water that will affect the pH. In yesterday's lesson, we talked about salts that are acidic and basic. Again, we had to take a look at what's in the water. Now I guess I could amend this. It's not necessarily just pure water, but there could be spectators in there. Spectators don't do anything to the pH situation. So when I say pure water, spectators can be in that pure water, and it still, will allow us to use these nice simple equations. So in the last, 4 lessons, we learned about the weak acids. We did some practice problems. We learned about the weak bases. We did some practice problems. We talked about how the Kas and the Kbs are related through the Kw. We then talked about the conjugate bases. We did some practice problems, conjugate acids. We then talked about the salts. And again, it always comes down to the question, what's in the water? We get our chemicals, we say it's in a solution, so we ask ourselves, what's in that water? Is it a weak acid? Is it a weak base? Is it a salt? Which means, does it produce a conjugate acid or a conjugate base? Which doesn't make any difference to the equation. Whether it's a conjugate acid or an acid, you're still going to use the same equation. And so it all comes down to what's in the water, and therefore, which of these two equations do we use? It's been that simple. Now today, we're going to now make the water not necessarily pure water. We're going to add some ions that are going to interfere with this equilibrium, which means these two equations will not work in a buffer situation. But that's okay, because we're going to derive two new equations. We're going to derive an acid buffer equation and a base buffer equation, which means I'm going to have 3 and 4, and we'll have 2 new equations to deal with these buffer situations. So 4 new equations with this entire unit. Tomorrow, when you watch the video on the titration curves, we will use one of the 4 for when we do our calculations. All you've got to do is think, what's in the water? That's really what we want to ask ourselves. And once we determine what ions are in the water, that guides us to the appropriate equation, and then we just solve it. Okay, so what is a buffer? And I am going to need you to write this down. You've already wrote the title buffer, so you can write down common ion effect in brackets underneath it. We've encountered the common ion effect already. It dealt with solubility. And it had to do with decreasing the solubility of an ionic compound when there was a common ion in it. And most of us completely blew that question. It was a horrendous attempt at that question on the test. I think if you go back, and maybe you already have, you'll understand what you should have done. Now in this case, the common ion is always going to be the conjugate of whatever you've put in to the solution. So it will be made up of a weak acid and its conjugate base, or a weak base and its conjugate acid. And again, just like weak acids and weak bases, I'm going to have two versions of a buffer, a weak acid buffer and a weak base buffer. So I'm going to have an H3O plus equation and an OH minus equation. Due to the fact that a buffer contains a mixture of an acid and a base, it's a very useful solution that can resist large pH changes when a moderate amount of acid or base is added to it. The reason we call it a buffer is because if you have this special solution, you can add strong acid to it and the pH does not change very much. Or you can add a strong base to it and the pH does not change very much. I don't know the term buffer, I guess a protection type thing. I guess that's the way I imagine it, because it's almost like this combination protects it from pH change. Now I guarantee in your biology you've talked about buffers. Yes? Talked about buffers in biology? Right? You may have done a little qualitative lab where you create a buffer, or maybe you were given a buffer and you add a little bit of base and you dip some pH paper in it or something. No, you didn't do such a thing? Sometimes they do that, sometimes they don't. We're going to do a titration on the Monday that I get back, and in that titration, a buffer will be established, and we'll be able to see that buffer, that buffering situation. So now essentially we've just got to derive the equations for our buffers, and then we're just going to use them. Okay. So just like for acids and bases, just like the pure water, weak acid, pure water, weak base, I'm going to derive a buffer equation here. And if the approximation is good, we use it. Again, this is just like the derivation that we've done before. We're going to have an ice table. We're going to solve the equilibrium expression, et cetera, et cetera. Again, this is liquid water. Doesn't come into the equation. Just like when we talked about the weak acid, we're going to start with some HA initial. And in the pure water equation that resulted in our two equations that we already have, there was none of this and none of this, and then we let the reaction go, and we figured out how much H3O plus was going to form. For a buffer, there is already some of the conjugate base in the water, and that's what makes this different. The reason a buffer works the way it does, if you add some base, this will consume the base and negate the effects of the pH change. And if you add some acid, this will consume the acid and negate the change in the pH. So it's like I think of it like a superhero of solutions. It has the ability to combat a strong acid if it's added, or a strong base if it's added. Okay, let's continue with the derivation. So we're going to assume it's going to shift to the right because there's no H3O plus. It'll shift in such a way to produce some of that. So we're going to have a minus X. We're going to have an X and an X. And so we're going to have HA initial minus X, X, and conjugate base initial, and that is plus X. And we're going to put it in the equilibrium expression, the Ka in this case, and I'm going to go straight to these things here. This is going to be X, and this one is going to be conjugate base, initial concentration plus X, and here I'm going to have weak acid initial concentration minus X. And again, if we were to rearrange and start doing our math, I'd have to FOIL that X through, and I'd end up with an X squared term over here. I'd have an X term over here. I'd have X's down here. There would be a quadratic situation. So if the approximation is no good, we would have to follow through on this entire equation. But if we assume that the approximation is good, because we're going to be dealing again with weak acids. If the acid is weak, then its conjugate base will be moderately weak. We'll have a small Ka. Which of the X's can I get rid of? If the approximation is good, which X's are small? Christian? The negative X, the minus X, that's basically 0. Yep. The plus X will as well. All right? We're starting with a significant amount of this and a significant amount of this, and if it barely shifts, then this is also approximately 0. Because this X will also be small compared to this conjugate base that was already added to the solution. Remember, this isn't being formed. It's in the solution to start with. So I've got a significant amount of conjugate base and a significant amount of acid. All right. Well, now with all of that gone, I essentially have Ka is equal to X times the concentration of the conjugate base initial over the concentration of the weak acid initial. Ultimately, I want to get the pH for this thing, and just as before, X is the H3O plus concentration, so I want to solve for X. So we'll bring that up there and down below. So X is equal to the Ka times the concentration of the acid initial over the concentration of the base initial, and that is equal to H3O plus. So the acid buffer equation to determine the H3O plus, that is going to be the Ka, because we're talking about an acid buffer, times the HA initial divided by the concentration of the conjugate base that's in their initial, and that gets you the H3O plus. Okay? We consider this to be an acid buffer because the Ka of the weak acid will be larger than the Kb of the conjugate base. Because sometimes it gets a little confusing. There's an acid and a base here. Am I considering this an acid buffer or a base buffer? And the Ka, if the Ka of the acid is greater than the Kb of the conjugate base, then it will behave as an acid buffer. The acid properties will dominate the solution. Let's now derive a base buffer. And you know what? It's exactly the opposite, which helps you in memorization. Let's see if we can come up with the OH minus equation by looking at our acid buffer and thinking opposite acid-base scenario. What do you think, Christian? Kb, concentration of the base, the weak base, initial, thank you. Yeah, divided by that conjugate acid of that base, that's correct. HB initial. That's it. That's the shortcut for that, if the approximation is good. Okay? You know what? For the sake of getting through example problems, you guys do that derivation on your own sometime. Don't do it right now. You don't have to do it right now. But I don't think it's going to be too earth-shattering. It's going to be the exact same thing, except I'll give you the I, right? We're starting with B initial. That doesn't count. I got 0 of that, and that's going to convert into, well, it's not going to convert. I'm going to start with some conjugate acid initial. And again, how do you decide whether you're going to use the acid buffer or the base buffer equation? You're going to look at the Kas and Kbs of the acid and its conjugate base, and the biggest one will tell you which equation to use. If the Ka is bigger than the Kb, it's an acid weak base buffer. And if the Kb is bigger, it's a base and its conjugate acid buffer. Let's do some examples. Good to go? Again, the derivation is identical to the other one. I don't think it is necessarily worth our while to go through that. My markers are dying. I'm running out of good markers here. Now, in my examples, I'm going to walk you through different scenarios that we've already encountered. So right now, this isn't even a buffer. This is a reminder of what we do if it's just a weak acid. And then we'll bring in the buffer, and then we'll talk about stressing the buffer, all right? Because we want to also talk about how this buffer can handle the stress of a strong or weak acid being added to it. Okay. So, I just have HF solution. What's in the water? Well, this is the equation, but let's ask the question, right? What's in the water? You tell me. Tell me all of the stuff that you know that's in the water in that statement. And it's really simple. There's not a lot in the water here. There's a very little amount that's in the water, little substance that's in the water. What substance is in the water? What compound is in the water? Christian's batting 1,000. What do we got? HF. HF is in the water. What is HF? What do we classify HF as? Sorry, Kristen? It's a moderately weak acid. What equation am I going to use? It is a moderately weak acid. Therefore, what equation is going to get me my pH, POH, blah, blah, blah information? Which one am I using? We'll go to the veteran because the rookies just don't, they're sitting on their hands today. Yep, except Christian. As long as the Ka is small enough, right? What is the Ka for HF? Ooh, and I shouldn't have used HF because I think it's going to be close. What is the Ka for HF? I think it's a times 10 to the minus 3 or something stupid like that. What is it? 3.5 times 10 to the negative 4, is it? Negative 4. Negative 1 over negative 4, I think, is going to get us into the thousands. Could somebody calculate that? Could somebody do a quick 0.2, divide it by that Ka, just to make sure? But as soon as I see it in the negative 4 or negative 3 region, it makes me a little nervous. Sean, what do you got? Oh, it's okay. What do we got? 571. Approximation is good for us. So the approximation is good, which means we can use this. Well, we know the Ka, we know the concentration, run it through, H3O plus, pH equals. I don't even need that other number. Let's be efficient here. When you're doing a test, by all means, write those little numbers in so I can see the little steps. But you know what? For this sake of this, I'll take the pH when you get it. Don't clear your calculator, right? Negative log answer equals. For all of us reverse people, all you got to do is put log and ignore the negative sign. So much more efficient on those old calculators. Christian, what do you got? 2.08. 2.08. Okay? So that's just a weak acid. I'm just kind of going over all the different things that we can encounter. Let's now change that and let's determine the pH of a HF F- buffer solution. And you know what? I should actually, because we have the shortcut, and I know many chemistry teachers, other chemistry teachers would say to me, oh my goodness, all these shortcuts, this is terrible. They should be doing the ice table every time. We know where it comes from. I want you to be able to use it. On the end, in first year university, you're likely going to encounter all multiple choice exams. They don't care how you determine the pH of their buffer solution, whether you show the steps or not. If you can use the equations, you're going to get marks. Okay, so, and I was kind of mean here, 0.2 in 1 liter. Ooh. That means the concentration of, well, let's take a look. In the water. What's in the water here? Somebody tell me some things that are in the water. Yep. HF. And actually, I'm going to now do the concentration of HF initial here. 0.2 divided by 1, 0.20 moles per liter or molar. I'll make it a capital M. What else is in the water here, Kristen? Sodium fluoride. That means I'm going to have some Na+. And what do I think about Na+? It's a spectator. And what else is in there? F-. F- definitely not a spectator. What's the concentration of F- in this water? It's 0.2 as well. Be careful. If I had made it something like calcium fluoride, all right, I would need to double it, right? Everybody aware of that little trick that can be in there? So this is 0.20 molar because it's a 1-to-1 ratio. I look at what I have in the water. I see that I've got the acid and its conjugate base. I'm thinking buffer. I go to my sheet and I look at the Kas and the Kbs for the acid and its conjugate base. They should be right beside each other. And now I'm asking myself, which is bigger, the Ka or the Kb? Which is the bigger number? In other words, is the acid conjugate base pair better at being an acid or a base? Really is what the question is here. Yep, Jess? The Ka is larger than the Kb. Ka is greater than the Kb. Therefore, this is an acid buffer. It makes it an acid buffer situation. We've already checked out the approximation. It's good. We take our shortcut for the acid buffer equation. Okay? That's how you determine what equations you're going to use. So therefore, I'm going to be using H3O plus, Ka, concentration of the acid over the concentration of the conjugate base. And I don't remember the Ka from the last slide. Yep. 3.5 times 10 to the negative 4, 3.5 times 10 to the negative 4, and then I'm going to have 0.20 over 0.20. That's coincidental, right? We have the same amounts. You'll notice it doesn't have to be. I could have had 0.2 and 0.3 or any other combination. But in this case, quite convenient, I can cancel out that. And so the H3O plus is the Ka, and therefore the pH is. Yep. That's the H3O plus. Take the negative log of that. 3.45. Okay? Now, it's obviously not as acidic as when it was just all a weak acid, because there's some weak base in there gobbling up some of that H3O plus. So the pH is rising a little bit. That's not surprising. That's okay. Again, the fact that they cancel out is coincidental. They don't have to. There's our pH of our buffer solution. Next, we're going to stress the buffer. We're going to add some strong acid or some strong base to this buffer situation, and we're going to ask ourselves, what's going to happen to the pHs? Okay, stressing the buffer. This is really just the next part of a question, because very often I will ask the question kind of in sequence, the way you're seeing it. What is it in pure water? What's the pH of the buffer? And then we're going to stress the buffer. So this is really part B, but put the title stressing the buffer. There's nothing wrong with that. In this case, we are going to need our equation, and we can write it simply in terms of HA. It doesn't matter. H2O to produce, in this case, H3O plus, and then the A minus. And when dealing with a problem like this, stressing the buffer, we do need to put the concentrations of the acid and the base in the equation. So I need 0.20 here, and I need 0.20 here. And in order to figure this out, we need a little note on the side here. I'm going to put one more line underneath here. But I'm going to put something here because I don't have a side to put it on. But in this case, the strong acid, in this case it's HCl, because it's strong, when you add the strong acid into the water, it's going to forcibly give an H plus to something in my water that's there. What's going to accept the H plus that's in my water from the HCl then? The A minus. So the strong acid, the HCl, will give an H plus to that base, right? And it will convert it into the acid. It will convert this into this by forcefully giving its H to that weak acid. The strong acid will give H plus to A minus and convert it to HA. So like I said, it's like the superheroes of a solution. If I were to reference a superhero, I would go back to the League of Justice back when I was a kid, and there was a superheroes called the Wonder Twins. Nobody knows the Wonder Twins anymore. They've gone by the wayside like Aquaman. Nobody really knows who Aquaman is anyway. Let's imagine then that these are the Wonder Twins. You have no idea who that is. But they're both superheroes, yet they've got these opposite abilities. In this case, we're adding a strong acid. What does the base do? It says, don't worry, I'll take care of that. I'm going to neutralize that acid by accepting all of those H pluses But in the process, it converts itself over to the HA, which means if I'm adding 0.1 mole, and we're going to assume that we're not worried about the fact that this is moles per liter, 0.20 minus 0.10, in other words, 0.1 mole of the base is being converted, 0.10, 0.20 plus 0.10, 0.30. So after the addition of the strong acid, I now have new concentrations of my acid and base. Again, what's in the water? There's going to be this much HA. There's going to be this much A minus. There's going to be some CLs floating around because of the HCl, but what is CL? It's a spectator. So I've only got this and this. It's still a buffer situation. I just need to put it in my buffer equation again with my new values. H3O plus. We've already determined that this is an acid buffer. Ka, HA initial over A minus initial. These are the initial concentrations before the equilibrium gets established. These concentrations were there, but then the HCl messed everything up, and now I've got a new initial concentrations. Ka, and I can't remember what the number is, and you guys will tell me in a moment, 0.30, 0.10, and times 10 to the minus 4, I'm recalling, but 3.5? 3.5. Yep. pH equals, 3.93. Let me do one calculation on the end. Let's do a delta pH. Could somebody tell me what the pH change was from before the buffer was added to after the buffer was added? So after the buffer, 3.93. What was it before the buffer, before the strong acid was added? What did I do? We got a mistake? .98, 2.98, and what was that pH from the previous slide before the strong acid was added? Not the buffer, but strong acid. 3.46, 3.46, and could somebody calculate how much the pH has changed by the addition of this strong acid? Yeah, Jess? -4? Did you say -4? Negative is fine, but the 4 is a little big. Yep. Negative 0.48. Negative 0.48. We have added 0.1 mole of HCl to a buffer, and its pH changed by 0.48 pH units. If I add that same acid to pure water, it means that I'm going to start with a pH of 7, and when I add this, I'm going to have HCl concentration of 0.10 moles per liter, right? And remember, this is strong, so they all fall off. That means my H3O plus is 0.10 moles per liter. What's the pH of 0.1? In other words, negative log of 0.1. Yep, 1. In pure water, if I add 0.1 mole per liter of HCl, I go from a pH of 7 down to a pH of 1, a change of 6 pH units. That's if I add 0.1 moles per liter of HCl to pure water, the pH dives way down, all the way down to 1. Now, we may be starting acidic already, but the pH change is only 0.48. So it's buffered against that pH change, that large pH swing. All right? In biological systems, I'm sure you guys talk about buffers all the time, something about natural buffers in the blood or something like that, that type of thing. Is that true? Am I saying the right things? And there's some kind of a natural buffer there that if you do have some kind of acid something, I know there's some biological function that will release acid and who knows what it is, acid something, I have no idea. Anyway, it's a good thing that buffer's in our blood or we would be in trouble. That's all I know. That's the message I get from my biology colleagues, that buffers are good, and I believe them. And this is why, because they protect that from large pH changes. Let's now add some base to this one. Same buffer as we had in a 0.2. This time we're adding base. When you're getting a question about a buffer being stressed, like a strong acid or a strong base added to it, just as before, we need our HA equation. We're still talking about the HF, F minus buffer, so we're still talking about that acid buffer because the Ka is greater. Again, I'm starting with 0.20, 0.20 as stated in the first part of the question. What's the addition of the NaOH going to do to my concentrations? What's the base going to do? Yep, Ben? It might. It could take an H from the H3O plus. You can consider it that way. That would cause this to drop, and then you would get a shift to the right. I don't like thinking of it that way. I like to think of it as our superheroes. The H3O plus guys, they're just kind of playing the game in the background. Think of it as our two superheroes. Who's going to swoop in and save the day? Tyson? And turn it into the A minus. In this case, so here's our little note, the OH minus from that strong base will take H plus from HA and convert to F minus. So in this case, the HA of the super twins steps in, donates the H, converts it to the A minus, which means, and I'm going to just save a line here, minus 0.15 plus 0.15. And therefore 0.05 and 0.35. Still the acid buffer. Even though we've added base to it, we still have HF in the water and F minus in the water. And the Ka for the HF is bigger than the Kb. So it's still an acid buffer. So I'm still using, H3O plus equals. Same equation. I just have new concentration. Are you sure? All right. .30. Delta pH again from the initial one, not from the one on part C. Sorry, part B, but from the initial one. So we were at 4.30 now. That's our pH 2. What was that initial buffer pH? Yeah, Christian? 3.46. And what's the difference? Yep. Positive 0.84. So it went up a little more than it went down the last time, but we added a little more base. But again, if I were to do a pH change of a strong base, it would be the same thing. We'd be going from 7, actually we'd be going less to 1 with 0.15. A huge pH change. Here it's been buffered. Yep. 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 Oh, these numbers in here? These numbers in here are coming from here. Yeah, because we've added the base, the negative is here because it's pulling those H's off and turning them into there. So when we add base, the acid gets converted into the base. And when we add acid, the base gets converted into the acid. Any other questions? Okay. I do have a base example, and what's that? All right. I do have a base example here, but here I've kind of put it all into one question. There was a Seinfeld episode that I saw the other day. You guys know of Seinfeld back in the 90s. Same type of gag they were doing. Someone would say something, blah, 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 and Jared would say, what was that? Nothing. I didn't say nothing. I'm sure you said something. I heard you say something. Anyway, frustration. So this example contains really the two steps that we looked at in great detail in the last one. First, we want to determine the pH of the buffer solution itself. Then we want to stress that buffer. So I'm looking for a pH change, which means I need two pHs. I need the pH of the buffer alone, and then I need the pH of the stressed buffer after adding the HCl. So let's first get the pH of the buffer, and then in the end we will get the pH of the stressed buffer. The stressed buffer is after the addition of the strong acid, the HCl. So we just want the regular buffer. What's in the water before we stressed it? I need a list of things that are in the water. And that's the first thing you always do. You ask yourself, what's in the water? Sean? So NH3 plus, all right, and how much is it? 0.33 molar. And we've got NH, and I'm missing the N, NH4 plus, and it's also 0.33 molar, all right? And you notice that you've got an acid and a conjugate base, or is it a base and a conjugate acid? So you're not sure. Go to your chart. Find those two things. Determine which is larger, the Kb of the base or the Ka of the acid. Which one's bigger? The Kb. The Kb is greater than the Ka. I don't need to see this when you're doing these calculations. This is what you're thinking, right? And therefore, it is a base buffer. Because the base part of it is dominating the pH scenario. It's winning the game. It's winning the game. OH minus KB, concentration of, what goes on the top in this case? Concentration of the base, because it's a base buffer, over the concentration of the HB plus, which is then that opposite guy. And do we have a KB for this one here? Yep. 1.8 times 10 to the negative 5, 1.8 times 10 to the negative 5. And oh, take a look. We set it up so that they're the same. Normally, a starting buffer, if you're making it like in the laboratory, you usually start it out by putting the same amounts of the acid in the conjugate base. If I'm making a buffer for a biology lab, which I often do, I make sure that I've got the same amounts. So you're obviously getting a POH in this case, and then ultimately a pH. Why? Because we work in the pH world. We don't work in a POH world for some reason. What do you got? 4.74?
pH.
You should have got the POH first.
Yeah, that's the pH.
That's the POH? It should be basic. It is a base buffer. We should be greater than... Tyson, what do you got?
pH.
Sorry? Just couldn't hear you. 9.26. We like it? 9.26? All right? Okay, so that's just the buffer. Now let's stress the buffer. And you really don't need to write out that B and that A thing. You just need to think of what's being converted into what. This is a strong acid. So what's it going to convert into what? What's going to be converted into what? I'm adding a strong acid to this pair. Which super twin is going to come in and save the day by mopping up all of this excess H plus and then being converted into what? That's really what we have to figure out. Pausing for you to think, because this is the key part. Actually, you know what? Without writing it out, I'd write it like this. I would rewrite my NH3, and I'd write 0.33 molar, and I'd write out my NH4 plus, and I'd write out my 0.33 molar, and now I'm going to subtract from 1 and add to 1. And the question is, which one gets the subtraction and which one, no veterans allowed, which one gets the addition? I'm adding H plus. Jenna, what do you think? Does it get taken? We're subtracting. So we've got a bunch of H's that are now floating around these guys. And you're saying then that this NH4 is going to grab up an H. Okay, that's fine, but that's the logic, right? So which one am I going to take away from? Yeah. This guy is going to grab up the H's and be turned into this. Maybe a little visual to help you. Because it's a strong acid, right? H plus does that type of maneuver. Adding an H plus into here, this thing's going to grab it up and turn it into that. Which means I'm going to have minus 0.10 and plus 0.10. It's the hardest part. Where to put the negative and where to put the positive. Once you've done that, you've got your new numbers and you're going to put it in the equation. You're going to be off to the races. And I'm kind of tight here on space, so I'll squeeze it in here. What does this make? 0.23, and then this one is 0.43. Again, it's still a base buffer. Just because I've added some acid to it doesn't make the Ka and Kb relationship any different. I'm still using OH minus, and I'm going to, again, I'll just put the number in 1.8 times 10 to the negative 5. And the B goes on top because this is a base buffer, 0.223, and over 0.43 I'm getting a POH, I'm getting a pH, and in the end, the question is asking me for the delta pH. How much did it change by adding this strong base? Sorry, strong acid. And I'll take the pH and then the delta pH if somebody has it. Again, we should still be basic, because even though we added all this acid and we would think that the pH should shoot way down to being an acidic, way down low, we still have our acid-base buffer here. And it's a weak base. Kristen, what do you got? 8.98. Delta? Negative 0.2? Negative 0.28. So again, a buffering effect. Didn't shoot straight down. Okay. So again, two new equations. You've got to ask yourself what's in the water, and a strong acid will always turn the base into the acidic form, and a strong base will always turn the acid into the basic form. Okay? No, whether you're dealing with an acid buffer or base buffer, it's the same maneuver either way. One little term about buffer capacity. As you might imagine, we can't just infinitely add acid, strong acid or strong base, and have the buffer do its thing. At some point, even the super twins will be defeated if you add enough of the strong acid or strong base. And again, you may have done that. Well, they used to do this in certain teachers would do this. I know in biology they would do a buffer thing. I think Mrs. Mayhead liked to do that lab. You'd add a little base, check the pH, and then at some point, boom, the pH would change greatly, right? You've reached the buffer capacity, so it can only handle so much. That buffer capacity is determined by the concentrations of the conjugate acid-base pair. So in the last example, 0.33, that particular buffer could only handle 0.33 moles per liter of acid or base. And once that was done, we would get a great swing in the pH. It would then be beyond its ability to buffer. Yeah. Even at the beginning, you'd use the equation to find the pH or POH. There would be nothing special there. You would have, now, I've not looked this up or determined this officially, but I would think that you would have a little more capacity on one side than the other. It would, sorry? Sure, you could easily figure it out. But the question too, what is the buffer capacity? If I were to say ask that question, it would be different for if it was the bigger number than it would be the smaller number, right? So if you had more of the base, it would have more capacity to handle strong acid. Now you won't have to worry about that, but that would be the case, right? It would have more capacity on one side than the other. When they're the same? Yeah. Like, let's say you added a little bit of the acid, right? Let's say you had a situation where you added some of this and now you had 0.23 and 0.43, right? This still has buffering ability until that runs out completely. So whether I start here or I start here, it doesn't really matter. right? What would the capacity be in this way? It would have less capacity for acid because I've now got less base to suck that up, right? So it doesn't matter. And actually, if you added base the other way, you could reestablish that buffer capacity. It would just swing it back the other way, and you'd be then ready to go again, right? So you'd be able to adjust that particular type of thing. I guess that's got to be what happens in a biological situation, right? So if your blood pH dips a little bit, another chemical has got to be naturally added to your blood to bring it back to its buffering ability, or if you ran out of buffering ability in your blood, you'd be in trouble. So it doesn't matter where it starts. You would just have varying amounts of capacity for acid or base, depending on where you're sitting. Okay. Practice problems, along with, again, an additional worksheet. I'll tell you right now that the textbook is much better than what it used to be in terms of these buffer questions. I probably don't need to hand out the worksheet anymore, but I already copied it, and so you might as well have a few extra problems. Again, if you feel you have it mastered, then that's up to you.